So live in class right now, students are talking in groups and they are discussing, as a reminder, when we look at these three different expressions and we think of that large capital N representing an expression, what do we need to consider when we determine the domain? So when I'm looking at that first one, which is the square root, and we have this large N underneath, I know that this value, when I evaluate this value, N must be greater than or equal to 0. So you can take the square root of 0. The square root of 0 is 0. It's possible. But when we take the square root and we put it into the denominator, remember that the denominator can never be equal to 0. So now N has to simply be greater than 0. It can't be equal to 0. We cannot have the value of 0 in the denominator. Also over here, we know that the value of N in this position can never be 0. So this cannot equal 0. It can be a negative value. It can be a positive value, but it cannot equal 0. Now, how is that going to help us? So let's look right here at our very first expression. And so what we're going to do is we're going to state the domain, and then we're going to graph it. As a quick review, we're going to graph it on the number line to the right-hand side. So I'm looking at this, and I'm comparing it to these three different rules, and it's going to apply to this rule. So I'm looking into the denominator. Because the denominator contains a variable, I'm going to write x minus 2. I know that this cannot equal 0. It cannot equal 0. So this cannot equal 0. I'm going to add 2 to both sides, and I get x. If I move down a little bit more, I go x cannot equal positive 2. So in the middle here, I have positive 2. It can be anything but positive 2. So I have a hole in the graph at positive 2. Any other value I could plug in, and I would get an output. The domain says what you're allowed to plug in that produces an answer for an output. Let's look at the next one. I'm going to press pause, and I'd like you to determine what is the domain and then to graph it on the number line. Here we go. So right now I'm looking at this, I'm looking at my three options, and I recognize I'm going to apply this rule. It means what's inside here, so x plus 1 has to be greater than or equal to 0. Let me move this down slightly. So it has to be greater than or equal to 0. I'm subtracting 1 from both sides, and I get x has to be greater than or equal to negative 1. Here is my negative 1. There's a line underneath. That means I include it as part of the solution set. Think of this as an arrow. As long as the variable is on the left-hand side, the arrow says shade to the right. I'm shading to the right. What does this represent? It represents that negative 1, we're going to include negative 1, and all values to the right, I could plug into this function, and I would be able to produce an output value. All right, let's look at example number 3. F of x equals x squared plus 6x plus 2. This is a tricky one. This is a tricky one. Because you're looking here and then you're looking down below and you probably are thinking like, well, which one applies? So the first thing I'm looking at is I see no square roots. So I immediately can eliminate these first two rules. The last rule says we only need to be concerned about the domain or what you can plug into a function if you have a variable in the denominator. We have no denominator. So in fact, we have no variable in the denominator. There's no restrictions. So this is going to be all real numbers. And there's a couple different ways we can write this, but this is one way to write it, all real numbers. If you remember how to write it in another notation, it may be like this. You could write out all real numbers. What would that look like on a line? We are going to shade everything from left to right. I am not restricted in what I can plug in. Okay, now we're going to jump into how does all of this domain and what you can plug in, how does it apply to this function specific to unit 8? F of x equals log base 2 of x. If you are slightly confused on what we are allowed to plug in, let's take this right now and let's think about this. I'm going to write this right now as just log base 2 of x, and you are welcome just to watch, okay? You're welcome just to watch here. So let's go ahead. So let's rewrite this in exponential form. Let's just start with, I don't know, let's just start with 0. So I'm going to put a 0 here. So if in this case, if the output was 0, what would the input have to be? So I'm going to rewrite this in exponential form, and I think you'll have a better idea. So remember when we did that silly little disco move? My son's like, please don't do that in front of people again, Mom. Sorry. So 2 raised to what power equals 2 raised to the 0 power equals what? So what is 2 raised to the 0 power? 1. So I'm going to make a little XY chart over here. And if my output was 0, my input would have to be 1. Now, let's do this again. Let's do log base 2 of x equals 1. So I'm going to write down and put here 2 to the first power equals x. So what's the answer? The answer is 2. So if my output is 1, then my input here would have to be 2. Because remember, x is always the input and y is the output. Let's switch this up, and now let's make this one more time. Let's do an easy one here. Log base 2 of x equals 2. So 2 to the 2 equals x. So I can see my output here. My output is 4, and my input is 2. I'm having a difficult time here reversing this and making this into a table. Just for 1 second here, I'm going to come back to this because I'm like I'm thinking over this, overthinking things. What I want you to recognize, and I'll come back and we'll make sense of this in just a second. If I switch this up and I make this into a -1, so if my output here is a -1, what does this look like? So then I would have 2 to the -1, and what is my answer for x? My answer would be, remember? Does anybody remember when you have a negative exponent, what happens? Yeah, we're going to take this value and write 1 over it. So here I produce a 1/2. So my x would be a 1/2. Here I produce a 4, here I produce a 2, and here I produce a 1. Let's do one more. Let's do log base 2, and what if it was a -2? What if it was a -2? So 2 to the -2 equals x. Again, just like Ms. Solano told us, we're going to take this value and I'm going to write it on the bottom. So it's 1 over 2 squared. The exponent then becomes positive, and that would be 1/4. So look at these values here. Look at these values. These actually represent, so these are all of the x values, and the y values are what I'm putting little boxes around. The y values are what I'm putting boxes around. So if I come back here, so I'm not so confused in doing this, because it's like a reverse order. So if I plugged in 1/4, 1/2, 1/4, 1/2, 1, 2, and 4, 1/4 was with -2, 1/2 was -1, 1 went with 0, 1, and 2. Let's look at what I'm able to plug in. The values I'm able to plug in are what? Can anybody tell me? If you were going to categorize these values, what would you say about these? Make a generalization. They're all what? They're all real numbers, but even more than that. They're all what? They're all positive. Are any of these zeros? They are never 0, which tells me that I am never able to plug in for this x value, the value that's directly behind the base. I'm never able to plug in 0 or negatives. So that is one of the rules. Just like we have rules here of domain, we're going to make another rule here. It doesn't matter what this value is down here. I'm just going to call this value a. This value right here, it can never be n, can never be negative, it can never be 0. So we're going to say it has to be greater than 0. It can never be 0, it can never be a negative value. So if I come back to this and I know that this value, x, has to be greater than 0, I come over here to 0, I put a circle and a line off to the right. Now, I did not actually put this example down, but I want to make another one here. Within your groups, I want you to show your tutor. So tutor, I think you could do mental math with this. If I said f of x equals log base 3 of x minus 5, think about the 4 different rules we have for now determining the domain. And which one applies? Which one of these apply? And then I want you to come up with what is the domain, and I want you to graph it. I'm going to press pause. So I'm going to get started. I'm thinking to myself, which rule applies? And we already know it's this rule. So what's behind the base, in this case base 3? This value, x minus 5, has to be greater than 0. So I'm adding 5 to the opposite side. I get x is greater than 5. I find 5. I put a circle because we're not actually going to include the 5. And as long as the variable is on the left-hand side, think of this as an arrow. It says shade to the right. What does this mean? This is a representation for us to say, what could we plug in and produce outputs? I could plug in 5.1, I could plug in 5.2, 6, 10, 100. Anything greater than 5 would work. Well, how do we evaluate each of these four? And that's going to lead us into practicing with identifying the domain of future expressions. So what I'm thinking here is I'm going to give myself just like a little question mark, and I'm saying 2 raised to what value equals 4, and I'm able to come up with that value. I know 2 to the second, so this answer to this expression is 2. Let's do it for the next one. 2 raised to what value equals 1/4, and this is often really confusing for students. So the first thing I think of is I need to get this value at the same level. I need to get at the same level. So if I put 1 over 2, now I can see the 2 and the 4 are at the same level. But I just moved the 2, and I need to be able to illustrate that move with this exponents. I know this value right here has to be negative because I just moved the 2 from the top to the bottom. The next thing I ask myself is 2 raised to what value is 4, and the answer is 2. So to evaluate this expression would be an answer of -2. Can I have a hand raised if you're able to get that on your own? Okay, very few of us. Let's look at the next one. So this rule, remember, whatever value is behind that base, this quantity has to be greater than 0. If this is not, we'd say this is undefined. This is another example. If this quantity is not greater than 0, we'd say this is undefined. All right, these 3 different logarithmic functions, we are going to identify the domain, and then we're going to graph the domain on a number line. So we're going to apply this rule, knowing that what's behind the base of the log needs to be greater than 0. So I'm just going to underline this. I'm going to come off the side. X plus 3 is greater than 0. This one's not difficult. So x is greater than -3. I come over here. I want you to understand this along as x on the left-hand side. Anything to the right of -3. So -2.9, I could plug in and I could get an output. -1, I could get output. +1, all of those would work. Now this is the tricky one. And some students might right away get a little bit confused. Remember, this is natural log. It's the same thing as log base e. I'm going to start by factoring this. So I'm going to come off to the side and say 1 times -6 is -6, combines to give us a +1. Okay, what 2 values multiply to give you -6 and combine to give you a +1? That would be +3 and -2 if I'm correct. Let me check. That looks good. So I'm going to rewrite this as f of x equals the natural log of x plus 3 times x minus 2. This entire quantity must be greater than 0. And now this goes back to, honestly, it goes back to the first and second units of the year. So I'm going to come and I'm going to set each one of these initially equal to 0. So x plus 3 equals 0 and x minus 2 equals 0. Okay, so -3. So I'm going to come up here. I'm going to find here 0, 1, 2, 3. There's -3. I'm going to make a circle. Why am I making a circle? Because I know that I'm applying this rule. And notice that with this rule, there's no line underneath. I don't actually want to use this as one of the solution points. And then I'm going to add 2 to the opposite side, and I get x equals 2. 2 is right here. Okay, so I have these 2. So here's my options. When I shade, because I don't have a double solution, it's either going to be shade, no shade, shade, or vice versa. No shade, I shade in between and opposite. So I'm just going to choose one point. We want to see if one of those points is true. I know this quantity has to be greater than 0. So x plus 3 and x minus 2, that has to be greater than 0. So I'm going to choose 0. 0 to me is the easiest point to plug in. So I'm testing this area right here. 0 plus 3 is 3. 0 minus 2 is -2. And I want to know, is -6 greater than 0? I just tested a point in here. -6 is not greater than 0. That means this is a no, and that means to the left and to the right of our points -3 and +2 would be yes. So if I plugged in anything to the right of 2, I could plug it in and I could produce an output. If I plug anything to the left of -3, I could plug it in and produce an output. Next one looks pretty complicated because we have numbers in front of the logs and we have numbers in back. But when we focus on the domain, we're only focused on this value right here. It's directly what's behind the base of the log. And so what I'm going to do is I'm just going to take x minus 2. I'm going to set it greater to 0, adding 2 to both sides. I have x is greater than 2. Here's my 2. I have a circle, and to the right. I created one additional problem. If you're watching this back because you're absent or need to relearn this concept, and so this is similar to an example from two previous ones before this. So I'm going to rewrite this as log base 6. Okay, then in parentheses, when I factor this, I'm thinking what multiplies to equal negative 42, combines to equal negative 1. That's going to be negative 7 and positive 6. So x minus 7 and x plus 6. I would take each of these factors or quantities. I know they're going to have to be greater than 0, but I'm going to initially set them equal to 0, and I'm going to solve. When I set them equal to 0 and solve, I get one answer of 7 and one answer of negative 6. I'm going to call this negative 6, and this is going to be positive 7. Now this quantity that's behind log base 6 has to be greater than 0. So x minus 7 and x plus 6 has to be greater than 0. And how do I know that? I know that because I'm applying this rule. The quantity directly behind the base has to be greater than 0 in order to produce an output. I always think, whenever possible, the easiest number to plug in is 0. So I'm testing all values between negative 6 and 7 by choosing 0. 0 minus 7 is negative 7, and 0 plus 6 is positive 6, and negative 42 is not greater than 0. So this whole area is a no. That means it's going to be a 0 to the right of 7 and a 0 above negative 6 and to the left of negative 6. So I'm looking at the first example, the top left here, and I'm going to solve this by writing in an exponential form. What does that mean? So if you've forgotten what that means, you're going to do that silly disco move. You're taking your pointy finger and you're pointing to the base of the log, which is a 3, and you're writing it as the base of this x, or the base of the exponent. And then you're raising your hand across. If you're doing that disco move, you're going all the way across the equation, across the equal sign. You're grabbing that 4 and you're raising up top like that disco move. Then you're coming straight back to your heart, and what we have behind our heart is x. So I'm asking myself, what is 3 to the 4th? A common mistake is people want to say 12. Remember, this means 3 times itself 4 times, which is 81. Let's move on to the one directly across from it, So my goal is to get it like this. My goal is to get it so that it's log of some number, log base of some number, and then the x or whatever the quantity is directly behind it. So anything else that's in front of it or in back of it, I need to get rid of. And as a quick reminder, when we solve for the variable, please excuse my dear Aunt Sally, I'm going to reverse this. My goal is to get this by itself on the left side of the equation. So I ask myself, on the left side of the equation where this is contained, is there any adding or subtracting to get rid of? There's adding. Opposite of adding is subtracting. So 2 log base 2 of x equals 6. Is there any multiplying and dividing to get rid of so that this is by itself? There's multiplying. Opposite of multiplying is dividing. Log base 2 of x equals 3. And now I'm directly back to where I was in this first example with solving for x in logarithmic equations. So I'm going to write this right now in exponential form. 2 raised to the 3rd power equals x. I know 2 to the 3rd is 2 times 2 times 2, so x equals 8. Let's look at our next example. Our next example, we are going to rely on the 3 rules from yesterday. So remember that we have 3 different rules we have to memorize. And these are the 3 rules. If you looked at your homework from yesterday, we consider this to be condensed form. This is expanded form. So when we go from expanded to condensed so that we can solve, adding turns into multiplying. The same thing here. When we go from expanded to condensed, subtraction turns into division. And then if we have a value on the outside, we can rewrite it as an exponent on top. So this is expanded. Notice we do have to have the exact same log base. So I'm taking these two quantities, and now I'm going to combine them or condense them. So these two are going to be multiplied. So back here I have x times x minus 7 equals 3. I've condensed the logarithmic equation. And this actually is in the same form up here as that we have in our first example. We have log base 3 of something equals 4. There's nothing in front or nothing way in back that I need to get rid of, so it's time to solve. But before I do that, I want you to turn to your partner or to your group, and I want you to figure out what is the domain of this and actually graph it on a number line. I'm going to press pause. Alright, so I know that this quantity, I'm going to apply that rule where I know that this has to be greater than 0. This portion has to be greater than 0. So first thing what I'm going to do is I'm going to take both the left and the right quantities and I'm going to set them equal to 0. So x equals 0 and x minus 7 equals 0. Well, I've already solved for 1, so there's 0. And then I'm going to add 7 to the other side, and I have 7. So here's 0 and here's 7. I'm going to put circles above them right away. Why am I doing that? Because I know this quantity has to be greater than 0. There's no line underneath, which means I'm not going to consider these points as actual domains. I know I can't plug in 0. I know I can't plug in 7. All right, so let's test a point. I cannot test 0 in this situation because 0 is one of those points. I can test anything in between them or to the left and right. I think 1's a pretty easy number to test, so 1 represents the values in between. So I'm going to take this quantity, x, and x minus 7. I know it has to be greater than 0, and I'm going to plug in 1. So 1 times, 1 minus 7 is negative 6. And then I ask myself, is negative 6 greater than 1? Yes or no? It's not. So I tested number in between. It doesn't work. That means that when I find solutions, the only solutions that are going to work, that are going to be part of the domain, would be anything to the right of 7 or anything to the left of 0. We need to know that before we get started. Now it's time for us to go ahead and we are going to solve this. So I'm going to go back and I'm going to use the space over here, and we'll redo this next problem later. And I'm going to have 2, that's my base. I'm going to raise it to the value on the opposite side, which is 3, and I'm going to set it equal to this quantity, which is x times x minus 7. 2 to the third means 2 times 2 times 2, that's 8. And I have 8 equals x squared minus 7x. Well, let's move the 8 to the right-hand side. So when 8 moves over to the right-hand side, I have 0 equals x squared minus 7x minus 8. I have a trinomial. It's a quadratic equation I'm solving. Remember that the quadratic formula always works when I can factor it. For me, it seems a lot easier. So 1 times negative 8, let's see if it's factorable. Do I know two numbers that multiply to give me negative 8 and combine to give me negative 7? I do. Negative 8 and positive 1. Multiply and combine. So 0 equals x minus 8 and x plus 1. Each one of these quantities called factors, I'm now going to set equal to 0, equal to 0, equal to 0, and I'm going to solve. So I believe that one answer is 8. I believe another answer is negative 1. Now, when I choose that, I have to go back and think to myself, do they both work? Do they both work? So this is what I see for my domain, but I actually want to plug it in as well to see does it work. So let's check. Is everybody ready? Here we go. Is 8 in this region? Okay, it is. Is negative 1 in this region? It is. Let's make sure right now it works. Let's come up here. 8 minus 7 is 1. 8 times 1, all I care is a positive number. Awesome, it's good. Let's do negative 1. Negative 1 subtract 7 is, negative 1 subtract 7 is negative 8. And then I plug in negative 1 here. Negative 1 times negative 1 is a positive 8. It should both work. So both of these quantities work. Neither one is what we would refer to as an extraneous solution. A common mistake students make, by the way, I want to come back down here. A common mistake students make is they don't produce this ahead of time, and they get these answers, and they're like, hey, remember, we can't have a value back here that's negative or 0. So they cancel out negative 1, assuming it's extraneous, before they take time to figure out what is really the domain. As I go through this problem, if you're feeling confident, feel free to work ahead here. So I first need to condense this, which means that this subtraction is going to turn into division. Notice we have the same log base 3. So log base 3 of x plus 2 over x plus 4 equals negative 1. Ooh, this looks like it's going to be tricky. This looks like it's going to be tricky. Now, what I notice is there's nothing in front of the log, and there's nothing behind here that I need to add, subtract, or multiply, divide. I can set this up right away. But before I do that, I need to think of the domains. So I know that this quantity, keep in mind, this quantity has to be what? Greater than 0. This quantity has to be greater than 0. Before we take time, because it's a fraction, let's go ahead really quick and let's figure out what we think our answers are going to be. So I'm going to come back here to the domain to make sure it works in just a little bit. I'm going to start by writing this right now in exponential form. So 3 raised to the negative 1 equals x plus 2 over x plus 4. Now, as Ms. Solano helped us with earlier in today's lesson, when you have a value raised to negative exponent, you can write 1 over that quantity, and now the exponent becomes positive. So I have 1/3 equals x plus 2 over x plus 4. And now I'm going to go ahead and I'm going to multiply this way. So 1 times x plus 4 is x plus 4. And I have 3 times x plus 2. I'm going to distribute and just do simple algebra here. 3x plus 6. And I'm just going to solve as quickly as possible for the value of x. So 4 equals 2x plus 6. If you see me make a quick mistake, just let me know. Negative 2 equals 2x divided by 2. I think I've made a mistake. Did I write something down wrong? Did I write something down wrong? I get x equals negative 1. Equals negative 1. X equals negative 1. I'm going to come back up here and I have to make sure if this is going to work. When I plug in negative 1 to this quantity, which is whatever is directly behind the expression, directly behind the base of the value, this has to be greater than 0. So I'm going to plug in negative 1 right now. I have negative 1 plus 2, and I have negative 1 plus 4. It has to be greater than 0 if it's going to actually be a solution. Negative 1 plus 2 is 1. Negative 1 plus 4 is 3. This is greater than 0. That means that this solution does work.